In this section, we look at a method that will take a differential equation and try to turn it into any differential equation and turn it into a homogeneous differential equation. And then we'll work for solutions from there. This is related to the previous section on undetermined coefficients. But before I do anything, let me introduce a notation we will use. This thing here that I'm going to be calling the derivative operator what it does, and it goes by capital D, it just simply means this: d of y is equal to y prime, d squared of y equals y double prime, d cubed of y equals y triple prime. You get the idea, etc. So, for example, dx equals 1, d squared of x will equal 0, d of cosine of x equals negative sine of x. D squared cosine of x is the second derivative, so I'll take the derivative of negative sine and I'll get negative cosine of x. D of e to the alpha x will be alpha e to the alpha x. D squared e to the alpha x will be alpha squared e to the alpha x. It has its own little algebra, and that's what we're going to work on in this section. So what we're looking for is a way of making things go to 0. Let me show you what I mean. If I take d of just any kind of a number, say d of 1, d1 will equal 0. So in particular, this operator annihilates the number 1. D squared x, for example, will annihilate x. D cubed x squared, that'll equal 0, because you're taking 3 derivatives, and this only has enough room for 2 before it becomes 0. You get the idea. If I wanted to get rid of x to the n, then I would take its derivative n plus 1 times. So that's a way of wiping those things out. Some other good things about this too, if I have this operator and I'm using it to work on f of x plus g of x, well, it's just like taking a derivative, so it does equal f prime of x plus g prime of x. Or what I mean is that this is df of x plus dg of x. And in fact, if there's constants in front of those, when you take derivatives of a function, you ignore the constant. So once I get that, I could rewrite it as c1 df of x plus c2 dg of x. This is important for mathematicians a lot of times because they refer to such things like this as a linear operator. And it works a lot like regular algebra. For example, if I try to do d squared times, well, let's just say d minus 1, for example. All right, and I'm doing that of the function f of x. Well, the first thing you'll apply is the d minus 1 part. So the d squared will hang there. And now you can distribute it in here. This is d fx minus fx. No d means I don't do anything. So take the derivative, and I'll have f prime of x minus f of x. And now you're going to take the 2 more derivatives of what's in there, and you'll end up with f triple prime of x minus f prime of x. Now, had I decided to do this in an opposite order, then doing the d squared first would have given me d minus 1 of f double prime of x. And then when I apply this d minus 1, like I said, it's like you distribute. You'll do d f double prime x minus f double prime of x. That'll equal f triple prime of x minus f double prime of x. And I didn't do enough derivatives here. I did 2 derivatives more than the one that was given there for this one, but I forgot to put a second derivative on this. The only reason I discovered it is because this thing is equal to this thing, and I knew that they should be. In other words, we could say that d squared times d minus 1 equals d minus 1 times d squared. In other words, they commute, just like ordinary arithmetic. That's very important. So we are going to try to figure out things that annihilate things. So for example, take a look at cosine of x. If I take d of cosine of x, I'll end up with negative sine of x. If I do d squared cosine of x, I'll end up with negative cosine of x. Well, notice this then. In other words, d squared times cosine squared of x plus cosine of x equals 0. Not cosine squared, just cosine. Or if I factor the cosine of x out, this is d squared plus 1. Cosine of x equals 0. So d squared plus 1 annihilates cosine of x. Similarly, if you were to do this process starting with sine, take its derivative, get cosine, but take its second derivative, and you'll end up with negative sine. D squared plus 1 also annihilates sine of x. Let's look at some more of them. D of e to the alpha x, when you take the derivative of this, you're going to end up with alpha e to the alpha of x, which is very close to what we had initially. Let me subtract the alpha e to the alpha x, and I'll get d e to the alpha x minus alpha e to the alpha x equals 0. Let me factor d out. Actually, let me factor the e to the alpha x out. And as you can see, d minus alpha annihilates e to the alpha x. So that's what we're talking about here. What about the next? What can you find that will annihilate, oh, say, x cubed plus 9x minus 1? Can you think of something that will annihilate that whole thing? Well, we know that if you take the fourth derivative of x cubed, it will wipe it out. But the fourth derivative will more than wipe out the rest of the other terms as well. Because the fourth derivative of 9x is 0, and the fourth derivative of negative 1 is 0. So you can see that d to the fourth will annihilate better than that. You could even say d to the n plus 1 annihilates any kind of a polynomial up to degree n. Let me do an example. I don't know which one I'm on. I'm going to call this example 1. Determine an annihilator for cosine of 8x minus sine of 8x. I sort of indicated before that the second derivative will wipe out, the second derivative plus 1 will wipe out cosine, and the second derivative of sine will wipe out sine of x, as long as you add the original to it. Here's what I mean. Let me take d of cosine of 8x minus sine of 8x. That's going to equal negative 8 sine of 8x minus 8 cosine of 8x. Now I'm going to do the second annihilator, or well, this thing here is a derivative operator, so the second derivative essentially of that same thing. That means what I'll do is I will apply it to this right side, and then sine will turn into cosine. I'll get negative 64 cosine of 8x, and over here I'll get plus 64 sine of 8x. And now let me factor out negative 64 from over there. Now if I add this 64 and all that other business to the left-hand side, I'll get d squared cosine of 8x minus sine 8x plus 64 cosine 8x minus sine 8x, and that equals 0. You can see then that my annihilator is d squared plus 64. So that's good. You can sort of construct them on an as-needed basis. Let's take a look at another one that pops up a lot. Something along these forms. Let's do d of e to the x cosine of x. That'll equal, now I'll use the product rule on this. So the derivative of e to the x, of course, is the e to the x. Cosine, you leave it alone for now. Then the derivative of cosine is negative sine of x. Now you can see, of course, sine and cosine always seem to work in tandem with each other. Let me do a second one. So if I do it again, I am going to once again take another derivative of e to the x cosine of x. So I get, use the product rule on just these two. E to the x, its derivative is still e to the x, leave cosine of x alone. Then we have minus e to the x sine of x. And now work this part here. We have negative e to the x sine of x, and finally negative e to the x cosine of x. Now notice what happens here. The e to the x cosine of x's go away, and we're left with negative e to the x sine of x. Now I could take this and subtract that, but it still leaves me with a piece of cosine of x. Instead, this is a very difficult method to come up with something that will work with this. What we have to do is remember the type of equations, or the type of homogeneous equations that had answers like this. So while I can play around doing all this, it's going to be hard to come up with something that eventually zeroes out. Instead, it might be easier to look at a situation where we actually had an answer that involved an e to the x and a cosine of x in its solution. Typically, we have seen things like this: e to the alpha x times c1 cosine, say, beta x plus c2 sine of beta x. So we had an equation. In fact, we had an auxiliary equation with alpha plus and minus beta I as zeros. That's how they happen. When we get these kind of solutions, that's how they would happen. And so we, in its most strictly split up form, the equation would have had a form like this. And that would, of course, equal 0. So let me multiply this all out and show you what it turns out to be. I'll get my m squared as normal, but then I'll have to do m times this part minus m times alpha minus beta I. And then I'll have to do minus m times alpha plus beta I. And then finally, I'll have this complex number times this complex number plus alpha plus beta I times alpha minus beta I. That's if I multiplied all this stuff out. Let's see what we get. M squared. When I take a look and try to combine my m's, I'm going to have negative m times alpha minus beta I plus alpha minus beta I. And then the last part, if you multiply this all out, you'll get alpha squared plus beta squared. FOIL it out. Here, the imaginary parts, I think I made a mistake there. The imaginary parts will cancel out and we'll be left with m squared minus 2 alpha m plus alpha squared plus beta squared. Okay, so that was when the alpha, and it was in front of the x for the e to the alpha x, and then either cosine of beta x or either sine of beta x would be that. So look at ours. If I want an annihilator, so to get an annihilator, for e to the 1x times cosine of 1x, what you have is your alpha is 1, so I'm going to, instead of n, when we do these things, we're going to apply a d. I'll have d squared minus 2 times alpha times m plus alpha squared plus beta squared. So this would be d squared, I put an m where a d should have been, d squared minus 2d plus 2. Let's try it out, just to show you it does work. So I'm going to do d squared minus 2d plus 2, and I'm going to apply it to e to the x times cosine of x. And like I said, you can break this up. D squared, e to the x cosine of x, minus 2d e to the x cosine of x, plus 2 e to the x cosine of x. That part will be untouched throughout the rest of the problem. Let me go ahead and take second derivatives of that first part. The first derivative will be e to the x cosine of x minus e to the x sine of x. And then on the second part, you have minus 2 e to the x cosine of x minus e to the x sine of x plus 2 e to the x cosine of x. And if I see anything that'll cancel out, I'll do it right now. Like I have a positive 2e to the x cosine of x, I have a negative 2e to the x cosine of x, so it's gone. And now let me apply it. Perhaps it might be easier to do it this way. And what do I have left surviving so far? I have plus 2 e to the x sine of x. And so let me finish off the differentiation here. I'll take the derivative of e to the x first. It'll do nothing. So I have cosine of x minus sine of x, plus, leave the e to the x alone and take the derivative stuff inside of here. I'll get negative sine of x minus cosine of x. And then let's see if it all, and then don't forget this plus 2 e to the x sine of x. Let me take a look at my cosines. I have a positive cosine and a negative cosine, so they are gone. I have a negative sign and another negative sign, so I have negative 2 sine e to the x plus 2 sine e to the x. So all of this is equal to 0. So I'll generalize this. You can probably do this yourself. D squared minus 2 alpha d plus alpha squared plus beta squared annihilates both e to the alpha x cosine of beta x and e to the alpha x sine of beta x. And it will annihilate any linear combination of those things as well. Annihilate let's say x squared e to the x. So let's start taking some derivatives and see what happens. Or let's take a look and see when something like this is a solution. Now, it'll be a solution when you see something like this, y sub c. You might see something like c1 e to the x plus c2 x e to the x plus c3x squared e to the x. If you see that as a solution, then you know that you had the number 1 repeated. You had it a total of 3 times. So this would have been m minus 1 cubed would have equaled 0. You'd had 1 would have been a repeated root. So then for us, d minus 1 cubed should annihilate x squared e to the x. Let's actually see if it does. Now, when you do this, you can apply d minus 1 3 times. So I can do like d minus 1 squared d minus 1 of x squared e to the x. And let's see what d minus 1 does to it. Whatever you do not make this d cubed minus 1. To do that is to violate anything that you know about mathematics. You have to multiply this thing out. Usually it's a lot of FOILing. All right, let's see what d minus 1 does. So first, the d part, I'll take the derivative of x squared. I'll get 2x. I'll leave the e to the x alone. But then I will leave x squared alone and eliminate e to the x. Now the minus 1 means that I put x squared e to the x. So you can see already the x squared part is gone. Now let me continue this. I'm going to do d minus 1 of 2x e to the x. Now because the 2 has nothing to do with derivatives of any kind, it just hangs around while you take derivatives. I can either leave it in here or I can factor it out front. I think I'm going to take it and factor out front. It just makes things a little bit messier, and I don't want that. So I have 2 d minus 1 x e to the x. 2 d minus 1. Now let me go ahead and take the first derivative of this thing and subtract it from whatever I get. So the first derivative will be e to the x plus x e to the x minus x e to the x. Well, those x e to the x's cancel. But you can see it's kind of whittling its way down. Now I have 2 d minus 1 e to the x. And we already know that d minus 1 annihilates e to the x. So that will equal 2 times 0 or just 0. All right, let's actually do some examples to show how this solves differential equations. So let me start. I don't know what example I'm at. I think I'll do example 2. Check that out later. But let's say we have y triple prime plus 2y double prime plus y prime equals 10. All right, the way this process works is the following. I'm going to convert to the d notation. So this will be d cubed plus 2d squared plus d, and you put y at the end. These are all derivatives of y, equals 10. Now what I want to do is, this here is a non-homogeneous equation. I would like to make it homogeneous. So I'm going to do one more d So this means d of d cubed plus 2d squared plus d y will then equal 0. Now I'm going to convert to m's. These are all derivatives, so when we go to the auxiliary equation, we have m times m cubed plus 2m squared plus m. That will equal 0. And I'm going to factor it and try to solve it like normal. M squared, I'm going to factor an m from all those things, times m squared plus 2m plus 1. Then what I get is m equals 0, 0. Now this part here is m plus 1 squared. So that part gives you m equals -1, -1. Now keep in mind what actually did solve the original equation, or at least the homogeneous part of the original equation, this d cubed plus 2d squared plus d, or the m cubed plus 2m plus m. That part there is responsible for one of these zeros and two of these repeated roots. So what you're going to get is, for your yc, this part right here will give us c1 e to the 0x, that's just c1, plus c2 e to the -x, plus c3x e to the -x. Remember, when you have a repeated root, you will, when you have a repeated root, you'll put an x in front of it like that. So that was the original yc. But then the second 0 that's in here, we actually want to do this right now. Let me get rid of this. That's going too fast right now. Let's just pretend we have all 4 of these as zeros. Then what we would write, part of our answer is we might say y equals c1 e to the 0x plus c2x e to the 0x. That would be the repeated root of zeros. Then c3 e to the -x plus c4 x e to the -x. Now once you have that, let's take a look at what constituted our original solution to the complementary part. That was the m cubed plus 2m squared plus m. That part there gave us the complementary part. And that consisted of 2 -1s and 1 0. So this guy right here plus these things right here are all part of y sub c. So what I was saying before, y sub c will be c1. I don't need e anything because e to the 0x is 1. Plus, and I'll just rename constants as I need them. But now one we picked up that was different from before is this cat. This is the guy, c2 sub c2x e to the 0x is my choice for my particular solution. Instead of a c2, I'll put a letter out that we associate with actually trying to figure out, and I'll put a capital A instead of a c2. So far I have my y sub c. Now I'm looking for a y sub p. So let's go back to the original equation. Now that I have my original equation, let me plug this ax in and figure out what a is going to be. Now, when we're done, I want to do this problem in a much different way. but let's go ahead and throw it in here then. When I throw ax in here, so my y sub p triple prime plus 2y sub p double prime plus y prime equals 10, then if I take the third derivative of ax, it's going to be 0. If I take the second derivative of ax, it'll be 0. The first derivative, however, will be just a. Well, that's pretty simple. A equals 10. With the a being 10, I know that y sub p will be 10x. So my y then will be 10x plus c1 plus c2 e to the negative x plus c3x e to the negative x. And there you go. Now, as a side note, when I actually do this problem here, I'll be honest with you, I don't like this. This is not my favorite method anyways, but the one thing that I can tell you right now is I could see just by taking 10x in my mind and taking its derivative, I'll have arrived at 10. So I knew 10x before I did any of this business. Remember, to get a yp, all you've got to do is find anything, and I mean anything, that you plug into this equation that pops out to equal 10. If you take 10x and plug it in here, you'll get 10. So anything that's simple like that, try it right off the bat, see how it works, and it should almost always work. Like if you have any kind of a constant here or any kind of a simple polynomial, it's usually pretty easy to do these things. This one you have y double prime minus 5y equals x squared minus 2x. So once again, I'll convert to d squared minus 5y equals x squared minus 2x. Well, to wipe out a second degree polynomial, you apply d cubed to it. And we'll end up with d cubed times d squared minus 5 of y will equal 0. Now treat this like an m equation, something like m cubed times m squared minus 5 equals 0. Here you'll get 0 3 times, m equals 0, 0, 0, and then the other one you'll get m equals plus and minus square root of 5. So for the 0 parts, when you're going to construct your solution, you're going to get a c1 plus c2x plus c3x squared, but then this part will give you 2 more, c4 e to the radical 5x plus c5 e to the negative radical 5x. Now, this here was part of the original homogeneous equation, so y sub c will be c1 e to the radical 5x plus c2 e to the negative radical 5x. And then over here, our yp, let me go ahead and put these together here. Our yp, we will use a plus bx plus cx squared. And we'll try to figure out a, b, and c. And of course, they go back into the original equation. So let's throw them in. We have y sub p double prime minus 5y sub p. And let's see what happens. If I take the second derivative of this polynomial, I will get 2c minus 5 times a plus bx plus cx squared. And so that would be 2c minus 5a minus 5bx minus 5cx squared. And this original thing was equal to x squared minus 2x. So it was equal to 0 minus 2x plus x squared. You can see I'm writing those underneath to make sure that I line up all of my coefficients. Well, this is pretty clear. Negative 5c equals 1. or c, equals negative 1/5. On the other hand, here I get 5b equals 2, or b equals 2/5. And finally, 2c minus 5a equals 0. Where'd my c go? Negative 1/5. So I get negative 2/5 minus 5a equals 0, or a will equal negative 2 over 25. And so my yp can be negative 2 over 25 plus 2/5 x minus 1/5 x squared. And then in combination with the complementary part, you get a full solution. Let's go ahead and move on to example 4. I'm trying to increase difficulty for each type of the problem that I do. And in this example, we have y double prime plus 6y prime plus 8y, and that equals 3e to the negative 2x plus 2x. Now you can handle these in separate pieces if you want. I don't think it's going to be too bad on this part. To wipe out the 2x is going to be easy, and it's also easy to take out the e to the negative 2x. So let's take a look at, I believe d plus 2 of e to the negative 2x will equal de to the negative 2x plus 2e to the negative 2x. And that'll be negative 2e to the negative 2x plus 2e to the negative 2x. And that will equal 0. So I can annihilate that part with just d plus 2. The 3 won't matter. To get rid of 2x, I simply need a second derivative. This right here, let's go ahead and rewrite that equation using d's. So I have d squared plus 6d plus 8 times y equals 3e to the negative 2x plus 2x. Let's go ahead and apply my annihilators then. Let's see what happens when I do d plus 2. I'm going to have d plus 2. When I apply it to the other side, 3e to the negative 2x plus 2x. That'll equal, I'll apply it first to this piece. I'll get negative 6e to the negative 2x. And then I'll apply the d to the 2x. I'll get plus 2. And then I'll multiply 2 times the 3e to the negative 2x. We know that's going to go away. Got it? And then finally plus 4x. And so then we cancel out the e to the negative 2x terms. That actually was supposed to have been a 6. So that cancels. And we're left with 4x plus 2. So then, if I want to wipe this thing out completely, I'll do a d squared to both sides now.
I'm sorry.
And that finally wipes out the right-hand side. So over here, let me go ahead and factor the left-hand side. I already have d squared times d plus 2. This piece here factors fairly easily. We have d plus 2 times d plus 4. Now let's go ahead and take a look at change of y, of course. Let me change this to m notation. I have m squared times m plus 2 squared times m plus 4. and that's set equal to 0. So my m, I'll have 0 and 0, and I'll have -2, -2, and then finally -4. Now the originals, we had -2 and -4 were all part of the original stuff. So from this piece, from these right here, I can form my y sub c. That'll equal c1e to the -2x plus c2e to the -4x. From the rest of these, I'm going to go and construct my y sub p. So let's go down here with it. Y sub p, I'll get a constant, so a, plus, and then I've got a repeated 0, so that's bx. Now remember, we had an e to the -2x was already a solution here. So when I have this repeated one, I'll need to add plus cx e to the -2x. And in some of the problems that you've probably been doing, you may have tried solutions of this form and it got zeroed out and it wasn't giving you the right-hand side. And then suggestions were to try something like this. Well, this only pops up when you do this method. Otherwise, it's a guessing game. So now I have a good idea on what I'm going to need to solve all this stuff. So let's go ahead and plug it in and find out what a, b, and c are equal to. So once again, I have y sub p double prime plus 6y sub p prime plus 8y sub p. All right, for this part here, I'm going to do it one derivative at a time. So I'm put a d in front of it so that I remember to take the derivative again. So when I do first derivative, the a will go away, but the bx will become b. And then for the second part, I'll need to use the product rule. So I get c e to the -2x minus 2cx e to the -2x plus 6 times exactly that stuff again. Got that. And then finally plus 8 times the original expression, which was a plus bx plus cx e to the -2x. And before I collect any terms, let me take this second derivative here on the first piece. I'll move my equals over to give myself more room. So I'll be left with, the b will of course go away. I'll take this derivative here. I'll get -2c e to the -2x. And then this derivative here will require a product rule. So I'll get -2c e to the -2x. But then when I take the derivative of the e to the -2x part, I'll get plus 4cx e to the -2x. Let me go ahead and multiply everything through. I'm going to try also to line up things underneath where they should be to make life easy for myself. So I'm going to get plus 6b, which there's no constant term in that first piece, so let me put this here. Then I have plus 6c e to the -2x. And then I have minus 2cx e to the -2x. And then finally I have plus 8a plus 8bx. I don't see any x terms in here yet. Plus 8bx. I'll try to slide that in there. And then I have plus 8cx e to the -2x. And see if I can combine anything. Well, I have 6b plus 8a, and then plus 8bx, and then this part here will be, I have -4c e to the -2x plus 6c e to the -2x, so that altogether will be plus 2c e to the -2x. And then as far as these pieces are concerned, I have to be careful though. Do you see this 6 right here? I didn't multiply it through. That should be a -12, which is nice because 4 plus 8 minus 12 all cancel each other out. So those go away. Now, what I'm supposed to be left with then was 3e to the negative 2x. So this is supposed to equal 3e to the negative 2x. Let me make that more like a dot than a multiplication sign. Plus 2x over here. So let's see what we have then. Well, easily I can see, based on this, that 2c equals 3, or c equals 3 halves. From these pieces here, I have 8b equals 2, so b equals 1/4. And finally, there's a 0 here, so 6b plus 8a equals 0, or my b is 1/4, so I'll get 6/4 plus 8a equals 0, or a equals negative 6/32. In other words, negative 3/16. So my y sub p then, my a is negative 3/16 plus bx plus 1/4 x plus 2/3, 3 halves, x e to the negative 2x. Now we're ready for the final example. This one here will be a doozy. There'll be a lot of work involved in it. I'm going to try to do step by step, very slow. And it looks like this. Y triple prime plus 4y prime equals e to the x cosine of 2x. Now, let me go ahead and convert this to d notation. So I got d cubed plus 4d y equals e to the x cosine of 2x. Now, to determine what annihilates this, you can use the formula that was given before, or you can simply remember how equations like this become zeroed out in a differential equation. E to the x cosine x 2x is part of a solution of the form we would have e to the x times c1 cosine 2x plus c2 sine of 2x. What that means is that I'm going to put in some numbers here. That was a 1. What that means is that 1 plus and minus 2i were solutions to a homogeneous equation. That means that in the world of m's, if I look at m minus the 1 plus 2i times m minus the 1 minus 2i, this will be the polynomial, or the in m's, that would have made sure that this whole quantity was a 0 for it, which in that case then, this easily would be a 0 for it. So let's see what we get when we multiply it out. I'm going to have m squared, and then I'm going to have minus m times 1 minus 2i minus m times 1 plus 2i. This is where the i's are going to wipe themselves out. And then finally, we're going to get plus 1 plus 2i times 1 minus 2i. So let's see what happens there. I get m squared. Here, you can factor an m from these two terms, minus m in fact, and you'll be left with 1 minus 2i plus 1 plus 2i. You can see that wipes that stuff out, but the i's at least. And the last part, whenever you multiply a number to its conjugate, you always get something like this. And the i's cancel out of there as well. So it looks like m squared minus 2m plus 5. So in d notation then, let's go back to the equation I have. I have d cubed plus 4d y equals e to the x cosine of 2x. Now to wipe that out, I am going to multiply both sides by d squared minus 2d plus 5. Of course, that makes the right-hand side equal to 0. Now let's go ahead and factor this to its fullest. I could factor it again, just like I showed you from before, but I'm more concerned with this stuff here for a minute. We have d squared minus 2d plus 5. Here I can factor a d out of here. And now let's take a look at all the zeros that can happen here. If I now convert to m notation, m squared minus 2m plus 5, m squared plus 4, set that equal to 0. Then this part right here, we already did this. M equals 1 plus and minus 2i. Here we have a 0. M equals 0. And then over here, we have m equals plus and minus 2i. So the ones that were originally in part of the y sub c are these guys. So we're going to have y sub c will be c1 e to the 0x, or just c1, plus c2 cosine of 2x plus c3 sine of 2x. Notice that there's no e that climbs in there. What this part here means, for the y sub p, I'll need an e to the x times, in the coefficients that I'm trying to find are those that will be attached to cosine of 2x and sine of 2x. Notice that this is the one that's going to give me an e to the x for my part of my answer. So let's go ahead and throw it in the original equation again. Y sub p triple prime plus 4y sub p prime. And let's see what happens. I'm only going to do these one derivative at a time. So I'm going to have d squared, and then I'll go ahead and take the derivative of this stuff. You'll get e to the x, using the product rule, where e to the x is times this whole factor, a cosine of 2x plus b sine of 2x, plus e to the x. Now I'm going to take the derivative of the stuff inside of there. We have negative 2a sine of 2x plus 2b cosine of 2x. That takes care of that one part. And I'm going to have exactly that stuff, but 4 times it. So I'll just copy and paste it in there. Before I do anything else, I'm going to do a bunch of simplifying here. And whenever I can simplify here, I'll automatically be able to simplify down here as well. So we'll notice we have an e to the x in both parts. So let me go ahead and put a bracket, and I'll take an e to the x, and I'll take it out, and let's see what we have. I have an a cosine of 2x, and then I have plus 2b cosine of 2x. Let me put those together. A plus 2b cosine of 2x. And then for the sine part, I have b minus 2a. And that's times sine of 2x. Now always try to keep in mind that there will be symmetry a lot of times between these things. Notice that I have an a and 2b, and then I have 1b and 2a. The minuses will not always agree because the derivative of cosine is negative, whereas sine is positive. So down here then, I can get 4e to the x times exactly that stuff. All right, and let me finish that parenthesis. Now, that part there, I didn't mean an equals, that part there will always just be, that'll write out the rest of the problem. So I'll just have to keep copying it and pasting it. I got to work this now. I'm going to take the next derivative of this guy. So you can see the convenience of the denotation. It'll sit there and wait for you until you get done what you need to get done. So once again, I'll leave the e to the x alone for the first part of the derivative. Okay, then I'll have plus e to the x. This time when I take the derivative of this part here, I'll get negative 2 times that stuff times sine of 2x. Plus 2 times b minus 2a cosine of 2x. And of course, the other stuff is just brought down. Next, let me go ahead and simplify as much as I can in there before I take the next derivative. So let's see what all is attached to cosine of 2x. Here I have an a plus b, but then I have 2b minus 4a. So a minus 4a will be negative 3a. And for the b portion of cosine, here I have just b, but there I have 2b, so plus 3b cosine of 2x. And then how about the stuff attached to sine? I'll start with, I'm going to stick to going in alphabetical order. I have negative 2a in front of this sine 2x, and then I have another negative 2a in front of that sine 2x. A correction. A plus 2b cosine 2x. Let's try that again then. So the a attached to cosine, I have a positive 1a times cosine, and then I have negative 4a cosine. So I do have the negative 3a. Now the b, I have 2b attached to cosine plus another 2b. That'll be 4b. And going on with the sine, I'd better get some sort of a 3b with the sine. Let's take a look. I have 1b times sine here, minus 4b times sine here, so that gives me negative 3b times sine of 2x plus, let's go ahead and throw in that other thing. I'm getting there. I got one more derivative to do. And as before, I'll leave the e to the x alone for the first part of the derivative. And then I'm going to have plus e to the x again, but this time I'm going to take the derivative of the stuff inside. So as before, I'm going to get a negative 2 times negative 3a plus 4b times sine of 2x. And I'm going to pick up a 2 in front of that stuff, plus 2 times negative 4a minus 3b cosine of 2x. And then, of course, I'm going to get the stuff that was left over from before. Now I think we can go ahead and try to get it all in one compact piece. Notice that e to the x is attached to absolutely everything. So let's go ahead and draw that out first. Now let's see if we can follow all these a's and b's and cosines and all that kind of stuff. So I think what I'm going to do, since I know I'm going to have a cosine of 2x and a sine of 2x, I'm going to have my cosine of 2x waiting for me. Let's see what's attached to it. So, and then I'll simplify after that. I have negative 3a plus 4b. And down here, I've got negative 8a minus 6b. And all the way over here, don't forget this 4 that's out here, I got 4a plus 8b. So that's all the cosine stuff. And then we have the sine. Let's do the same thing. When all is said and done, I better see some symmetry here. Let's see what's attached to sine. I have negative 4a minus 3b. And then here I have 6a minus 8b. And then finally down here I have 4b minus 8a. All right, let me go ahead and see what all we got attached to cosine. I got negative 3a minus 8a plus 4a. So negative 3 minus 8 is negative 11, negative 7a. Then my b's, I have 4 minus 6 is negative 2 plus 8 plus 6b. That's attached to cosine of 2x. And then for the stuff attached to sine, let's see what I have for the a's. Negative 4a plus 6a, so I have 2a. 2a minus 8a is negative 6a. So there's symmetry right there. I better see a 7b in here somewhere or I'll be sad. Negative 3b minus 8b is negative 11b. Negative 7b. Very nice. And remember, all of this was supposed to turn out to be equal to e to the x times 1 times cosine of 2x. Of course, that means that there was a 0 in front of sine of 2x. So let's set them up. I have negative 7a plus 6b equals 1. And then on the other hand, I got negative 6a plus 7b equals 0. If you don't mind, I'm just going to do a little bit to this. I'm going to make it negative 7a plus 6b equals 1. And I'm going to that was a negative down here anyways, I don't know why. I want to multiply this by a negative just to take the minuses out. Now, I want to find a and b. I think the easiest thing to do is to multiply the first equation by 6 and the second equation by 7, and that'll wipe out the a's. So if I multiply this first equation by 6 and the second equation by 7, I will get negative 42a plus 36b, and that'll equal 6. And then over here I'll get 42a plus 49b will equal 0. Add these two together, and it looks like I'm going to get 85b will equal 6, or b will equal 6 over 85. Now you can take that, plug it in, and find the other value, but I prefer to start back here again. This time I'm going to want to wipe out the b, so I'm going to multiply the first equation by 7, and the second equation by negative 6. This will give me 42b's and a negative 42b in both cases. So what do I get? Negative 49a plus 42b equals 7. on the next one I get negative 36a minus 42b equals 0, and I'll add them together. B's, of course, will cancel. I get negative 85a equals 7. So a will equal negative 7 over 85. So this gives the solution y sub p equals e to the x times a cosine of 2x plus b sine of 2x.